Hello folks, this is Tom from anti-proton.com, and today we are going to discuss uranium glassware. Uranium, when most people think about it, they think of a big chunk of rock like this. This is a piece of uranium ore from Moab, Utah. I'm wearing the gloves because uranium is somewhat radioactive, not very radioactive, but it is chemically toxic like lead. And so it's a good idea to either wear gloves or wash your hands if you hold it. The actual radiation itself that comes off of the uranium is negligible, as you can see. For thousands of years, humans have used uranium for coloring as well as other things. The reason is because uranium allows for various oxidation states of the chemical, which produce vibrant colors: reds, browns, greens, blues, yellows. As a result, uranium has been used in everything from Roman bath tiles to pottery to dishware that people ate off of in their homes in the 50s and 60s. Yep, that's right, uranium, just like this guy right here. And no, I'm not going to get cancer from this by next week. The radiation dose rate that comes off of this is so low that it's only weakly carcinogenic at best. However, if you were to inhale the dust from this, that would significantly raise your cancer risk, as would the radon gas that is emitted from uranium. So it's important to be mindful of this when you're handling uranium. By the way, the dish is also radioactive because it's colored yellow by uranium. So let's take a peek at some beautiful uranium samples, like for example this one. But instead of taking a peek at, oops, see if you can even see that. Instead of looking at the actual ore, let's instead turn and look at the dishware, because that's sort of the point of the video. This is backed by popular demand, by the way. People love the dishware. Before I can do anything, I'm going to set up a gamma spectrometer so that you guys can see along with me what's in each sample right on the fly as we look at it. Sound good? To do that, we'll use our B Research spectrometer. Here it is. All right. Okay, so we're set to go here. We have a Polymaster. This is a 1703 GMB. It's a neutron detector and gamma ray detector. And that's currently reading right up here on the screen, so you can see that we are at 23 counts per second of gamma rays and 0.18 counts per second of neutrons. Our background is approximately 0.23 microsieverts per hour. Not too much. This is a Ludland scintillation probe with a sodium iodide detector, 1 inch. It's currently on the times 100 scale. So you have 0, 10,000, 20, 30, 40, and 50,000. So 0 to 50,000 counts per minute is what you're looking at right here. And then this 1.5 inch sodium iodide detector is connected to a scintillation, it is a scintillation counter. It's connected to a gamma spectrometer, specifically to the B Research one right here. And that's going to be appearing right here on the side of the screen. So let me let that appear for a second. And we'll start that over again. There it goes. It's building a spectrum of whatever just happens to be around us. And to give you an idea of how that works, if I were to take a sample of cesium-137 and put it right in place, you can see very quickly the cesium-137 responds and appears right on the gamma spectrum, right? There it goes. The detector here responds, the detector here responds, everything's responding. The same thing would happen if I were to take, if I were to start this over again and I were to take cobalt-60. You get a new sticker for that one. But something like cobalt-60 might take a few more seconds to resolve. Anyway, alright, so you can actually see the peaks forming for it, but we're not going to worry about the resolve time in that. So let's stop this for a second now, and let's look at the uranium glassware. First up on the list, and I'm not a historian, if you know what these pieces are, tell me, please. Ironically, my father is a historian, I'm not. This guy right here is the first piece I picked up. My point is to show you the radioactivity of them more and to talk about them more than to actually talk about their history. Most uranium glassware that I have here has uranium that is natural and refined. So it contains uranium-234, 235, and 238 isotopes, almost entirely uranium-238. 99% about of uranium-238. This is not going to explode. It's not fissile. You can't make nuclear weapons out of it or anything. They made thousands, millions of these things. In fact, during the 20s, 30s, and 40s, right around the Depression time, you could get this in a box of like soap or oatmeal or whatever, and it was called depression glass for that reason. People would actually buy these boxes of soap and oatmeal and all these other various things just to get entire sets of these because it was expensive to get decent looking glassware or dinnerware, and this was a cheap way to get it. And look at it. It looks absolutely beautiful. I mean, if you didn't know any better, you would think it was the most amazing thing. And to cut the light off for a second, you'll see when you put a black light up against it, it shows, hopefully you can see that, maybe you can't. But by the way, this is a nice black light I have right here I got. You can see it actually shows up nicely. And if you could see this with your own natural eyes, it would look even better. The radioactivity in these samples is not very high. To give you an idea, if we put this detector in the times 10 modes, now we're 0, 1, 2000, 2000, 3000, 4000, 5000. Our background is around 3000 counts per minute. If I put this up against it, our gamma background barely goes up at all. If I put it against the polymaster, we're at 19 counts per second. What do I get? Almost nothing. The reason we're not getting much of a change is because this doesn't really put off too many gamma rays, and you notice it's not putting off any real neutrons either. They're there. There's radiation. With a Geiger counter set that, like this guy right here, that can show you alpha, which is alpha particles, 2 protons, 2 neutrons make an alpha particle. Let me open up the back of this thing. You can probably hear the difference. But that's alpha particles. How do we know it's alpha particles? What's the best way to know? Take something like this TI-83 Plus technical manual, put it in between, and it stops. Alphas are stopped very effectively by paper. There's some beta radiation coming off of this, which we can block most of with a little piece of copper like this. If you were going to test it, you could do that. So if you put paper up against it and you saw that it lost some counts, you could guess that those were from alpha. If you put up a piece of reasonably thick aluminum or copper and you see the counts go down, even more so than the change in counts would tell you how many betas you were getting, and the remainder that's still making it through is going to be gamma rays for the most part. And there's going to be some X-rays emitted from this too. So let's move and show you another piece. By the way, that's not even enough to put out a gamma spectrum, so I'm not even going to worry about showing you one right this second. If you were to look at the screen, let me put it back for a second. You'll see that you're getting nothing but background. That's what that huge peak is. Huge big peak right here in the middle is nothing but background. Alright, so let's look at the next sample. This guy right here you've seen before. I'm going to show you some new stuff too, so don't be all like, oh, I've seen this before, blah. This guy right here I just love this thing. I don't know, it's elegant, it's beautiful, it's not particularly radioactive. Again, it's not doing anything to the detectors. Oh, it'll make the Geiger counter dance a little bit, but not much. 3,000 or 4,000 counts per minute is all you're going to get from it. Alright, let's check something new. Now, I just got this in the mail. Alright, this piece came from the Netherlands. This right here is Marigold Glass. It looks like canary glass to me, actually. And I got this from BT. Well, we'll call you Buddy, because that's the first part of your name. I never can decide whether or not I should put people's names out in here. So, Buddy, if you watch this and you want your name out, just go right ahead and reply with a comment, and I'll be sure to slap your name and everything right on the site. But as you can see, this is a more potent piece of glassware. At 16,000, 16,000 counts per minute alpha. Maybe a little higher if I get the back just a little closer. Come on, a little more, a little more. It's just pretty potent for a small uranium dish. we put it on top of the polymaster, you notice we all of a sudden get 80 counts per minute, 90 counts per minute. Neutrons don't really do much. But this guy right here is definitely putting out more than we got off of the other ones. It overruns the Ludlum. I just changed this to times 100, so 0, 10,000, 20, 30,000, 40,000, 50,000 counts per minute. 3,000 is our background. 14,000, 15,000. So about 12,000 counts per minute on the Ludlum. And let's put this here. Right like that. And let me start over. Here's the gamma spectrum forming. And if you watch the gamma spectrum form, we hopefully will see some uranium coming out of this guy right here. Alright, what are we getting right here? There's a peak forming. That's probably uranium-235 that you see right here close to 200 keV, like 195 keV. Probably uranium-235. You would get uranium-235 and some uranium-238 you would detect inside of this if it were natural, which it is. I've already run this through a spectrum. But you're not going to get a lot of the other isotopes that are in here. They will eventually build up. Over a long time, you'll start getting bismuth-214, lead-214, all the other isotopes radionuclides will start to build up. But they're not very prominent right this moment. As this isn't that old. It hasn't had a lot of time to get into isotopic equilibrium. But this is definitely refined natural uranium. So you can see the spectrum forming right there. That's uranium-235 that you're probably seeing right there. This is the big long peak you see at the very top. Comes from background and probably thorium. Here, let me show you what the spectrum looks like when I spent some time and made this spectrum a lot better in detail. Here it goes. We're done with that. Moving right along, I have some little stupid things like this ashtray, which doesn't do much of anything. The Ludlum, I mean the polymaster doesn't even really detect it. It barely even puts off alpha. But it looks nice and glows nicely, so you can put this on your desk safely without any particular harm. I should know I do. It's just not radioactive enough to do anything. Now, we have some weirder stuff, like this crazy looking thing. Look at this. Look at this little dish. I love this little dish. It's so neat looking. It's not particularly over the top. As you can see, the polymaster barely responds to it. No, this isn't getting like contamination on the probes. These glass sources are pretty sealed. It has some alpha. It's a little bit stronger than my other glassware pieces, but nowhere near the Marigold. Marigold's taking the cake right this second. You get a couple thousand counts per minute off of this. But not enough to shake a stick at, as the expression goes. $1,800 counts per minute, 2,000, 22. Not much in the way of counts per minute, but neat to look at nonetheless. Alright, we're getting kind of close to it. Here is a big bowl. Now this is a crazy thing because my father and my stepmother own this. And I borrowed it for this. The problem I have with this is that they keep using it for food. I keep telling them they should know better. Don't use this for food. In fact, our last Thanksgiving dinner, they filled this thing up with meatballs. And I wanted the meatballs, but I couldn't eat them because they were in uranium dishware. Now you might say, Tom, are you being a radiophobe? Are you afraid of radiation? Well, obviously not. It's not really the radiation that's the problem. Although, don't get me wrong, I don't want to get any of the alpha-emitting uranium particles that could be in here, like little individual uranium atoms can dislodge in the same way any other powder can come off, and they could get in the food. But I'm worried more of the heavy metal toxicity of these. It's kind of like leaded glass. You shouldn't use leaded glass with something like tomatoes, just because the acid in the tomatoes can leach some of the lead out. The same thing works for uranium. It's a heavy metal. Again, this is not particularly powerful. This is not going to irradiate your house. It's not even enough to show up on my scintillators. But it still looks really nice. But let me show you, well, let me show you one more, and then I'll give you the really, really powerful piece. This is a really light piece of, it looks like it could be canary glass, but it's very light. It's definitely radioactive, but not very strongly. And it doesn't glow under a UV light. And they don't all glow under a UV light. Only certain oxidation states of uranium will glow nicely under a UV light. So not everything glows. This guy right here is my ugly plate. This right here is my nice looking plate. You can see which one people would have wanted to get in their cereal box. Actually, I wouldn't want to get any of these in a cereal box, but people did. So then, what else can uranium look like? Well, it can also look like this. This is a piece of, I've never been able to decide if this is Fiesta or knockoff Fiesta. I think it's knockoff Fiesta because I don't see a Homer Laughlin mark that you should see on this. Back in the 30s, these were very popular. I use Fiesta ware today in my house, but it doesn't have uranium glaze as the dominant colorant like this one does. And only the white and orange ones from that time period were uranium. But they were certainly hot. 24,000. 24,000 counts per minute. Not bad. Not bad at all. Mostly alpha, though. Technically in counts per minute, though, this guy's winning out. When it comes to counts per second here, 66 counts per second versus the 90 plus we got off of the other one. Yeah, this plate is not actually as strong as this plate is. Let's check the scintillator out. We're in times 10 mode, so 0, 10, 20,000, 30,000, 40,000, 50,000, right? $10,000, $12,000. So about 9,000 counts per minute if you subtract background. Not bad, not bad. And let's see what this looks like if we use the scintillator on it. All right, starting over. Better hold that. I don't really want this to fall. And again, you're going to notice that this looks a lot like this plate did. And the reason is because they use exactly the same colorant. There's a different chemical state that this colorant's in. It's a different oxidation state of uranium. But the actual radionuclides involved, uranium-235 and 238 primarily, as well as some thorium, protactinium, some other things like that, they're all basically going to be the same. As you can quickly see, the spectrum looks the same as before. Background is in here. You can more easily see the peaks between the thorium and the background. You can see uranium-235 showing up. Not bad. Not bad at all. Let me show you a spectrum of what this one looks like, by the way. Here's a better spectrum of it. Definitely some nice samples of uranium glassware. I've seen better samples of uranium glassware. I do not have the best collection that's out there in the world, but still, it's not a bad little collection. So let me take these two plates right here that don't fluoresce, and I'll leave them out. I'll leave them out for you. I'll show you all the fluorescing ones in just a second here. You kind of move all of these over here. Let me sort of move this out of the way. Put these all together. Cut off the lights and see if we can get some fluorescence. Alright, so oops, we take our black light over top of this, you see the fluorescence. In my eyes, because I'm a human being, I have powerful human, eyes that the camera doesn't have. All of these dishes are glowing beautifully back at me. But the reality is that you can't see them very well. So let me take this more powerful UV light and hit them with that. Do you see? even the big one. Just trying to reflect the light off of something. But as you can see, they definitely all fluoresce. This one fluoresces very well, the one I got from Buddy. It looks absolutely beautiful when you hit it with the black light. I'm hoping I can get a good view of it. God, it makes my hand look so weird. But anyway, see? That is the most amazing part of depression glassware. It's the light you're seeing off of it is mostly being generated by the uranium. The black light hits the uranium atoms, excites them, and they emit fluorescence. Basically, they emit visible light as a result of that. How wonderful is that? However, as you can certainly see, certain glasses, even though they do contain uranium, which I've proven this does with gamma spectroscopy, do not fluoresce. So you can't just use the fluorescent light to prove that it's there. But if you take a fluorescent light like this to a junk shop, you can certainly find these things. The light does not absolutely guarantee it's uranium. It's a very, very good indicator of it. Very good indicator of it. Anyhow, so this has been Tom from anti-proton.com. I think these are perfectly safe to own in small amounts in your house. Don't eat off of them. Don't put them, by your bed or anything. But if you have this sitting on your mantle over your fireplace where the family can look at it, I don't see anything wrong with that because it's not particularly radioactive. It's only weakly radioactive. It's barely even a carcinogen in its current state. If it were to break, however, make sure you don't inhale any of the dust. Go there and put some damp cloth over top of it and clean it up very carefully without getting any of it in your fingers or inhaling any of it. Because once it leaves its normal solid glass form and gets in your lungs and your bloodstream, that's when it becomes a problem. So again, this has been Tom from anti-proton.com, and bye-bye.